Okay, so we're going to start with our revision on electromagnetism, but today we're going to focus on only two core topics, which is the first one is the force on the current carrying conductor in magnetic field, which is the motor effect. The second is the electromagnetic induction. So we're going to practice more about KaDi KiMo in this question, in today's question, and hopefully it strengthen and um, make your understanding more stronger of this particular topic. So let's start with the first question over here. Diagram 1 below shows an arrangement to study the effect of magnetic field on a copper rod carrying current. So the bare copper rod is free to move along the bare copper rail. So this is another typical type of setup for motor effect. So A, on the diagram, mark and label with B the direction of the magnetic field. Okay, so direction of magnetic field is from north to south. So this is basically the north, this is the south. So north to the south, B. Okay. B, when the copper rod move along the copper rails, the diagram mark and label direction of current I through the copper rod. So let's see we at the bottom current from positive to negative. So this is the direction of current and then it flows to the negative terminal. So this conductor connected to the battery. So copper rod, so the conductor, electrical conductor, when they touch, current can flow from copper rails to the copper rod. So the direction of current is actually into the ring away from our eye, and the current will flow back to the copper rails others and return back to the negative. And label as the direction of the movement of the rod. So this and that you have to use, you have left and right. So again, KaDi. So we are in the motor due to we have battery over here. So we are motor effect. We should use left hand rule. I mean left hand rule. So the first thing that you need to do is align the magnetic field. So south downwards. So I do that like that. So the current now is into my eye, but we already shown that the direction of the current is away from the eye. So we just rotate it like this. So it's away from my eye. So the force is actually to the left. So the force is explain how the motion of the copper rod is produced. So this is due to the catapult field. The electromagnet current carrying conductor with magnetic that produce catapult. So that is how the motion is produced. So due to the catapult field by interaction of the electromagnetic carrying conductor and the external magnetic field. So I just need to be just sit the external sound accurate here. External catapult field. D. What happened to the motion of the copper rod, and explain your answer. The rheostat is adjusted until its resistance decreases. So our answer is cos D. Okay, that means we need to explain, right? Yes, because current is so increase because current is increased. So again, Fleming left hand rule. So we change the current by reducing the resistance. So the current can flow more. Thus, the force, the magnitude of force is bigger. So the rod should be moved further to the left. Increase because current is increased. So we can say that the copper rod will move further to the force is increased. So to the left as force is the force is increased because is increased as well. Okay, the battery is replaced by AC power supply. So this is a very challenging question. Before this, we just use AC battery for motor effect. How about AC power supply? What will happen to the copper rod? So basically, the copper rod will oscillate between left and right. The copper will oscillate. Right. Current continuously changing. So that is the rho XT, which is the current. So that probably is student. And then the second will be out of stage. The first force is to be to the left, and then the force will be to the right, and then process is as long as it connected to the power supply and the is closed, the rod will sway or move left to left. We call the movement is oscillation. One is which is the principle involved in the so this in here we say that DC. So that's the only application that we learn for this subtopic. Number two, the diagram shows the structure of a direct current motor. Name the part labeled P. That is the simple name, but it also has split ring commutator. It's the more complete name. If you want to commutator, just commutator is also acceptable. Split ring, cross ring is split into half. Q is brush carbon or carbon brush. What is the function of the part label P to change direction of current every half rotation? We need to change the direction of current that the force, the rotation will only in one direction, the force on causing the rotation to be in only one direction. Q to provide electrical contact. Okay, see, label the direction of the coil. So we have positive and negative. So direction is from here to here. So here, 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 and here. Okay, that is the direction of current. State and label direction of the force acting on the SV side of the coil. So this coil over here. Rule that we need to use, again, the question already stated about motor, so we just need to use the left hand rule. We don't need to check either they have a battery or not. That doesn't matter here. But if you want to, you can. It's obviously there, the cell, but the question already told us about it is about DC motor, so we have to use the left hand rule here, plainly left hand rule. First step, align your magnetic field to the south pole, which is on the right, and then the current now currently into my eyes. But we already draw the SV current is into the page, so we just play into the page and make sure that you retain the direction of the south pole, so the force is down. So we can make it clear, shall we? So downward, and then automatically this force over here is upward. Again, we can add north to south, align that first, and then the current into my eyes, and then the force is upward. So we guess it correctly. Or rule. You can just pick one, and then the other one is gonna be direction. This is downward, this is upwards. So number 3, name the rule used to determine the direction of the force. Make sure that you spell correctly for Fleming's, and it has apostrophe. What is the direction of rotation of the coils? You can see this one is downward, is upward, rotate like this. So it's counter. Counterclockwise. Okay, number 3. Diagram shows the arrangement of an apparatus to investigate the interaction between a current carrying conductor and the magnetic field. So this is a mode. How I know that? Because of magnetic field and a current carrying conductor. Or we can say that it has battery. So end of the story here. So the type of magnet is used. Magnet or magnet. Or permanent magnet, or C-shaped magnet, whatever, doesn't matter. Doesn't put it electromagnetic or something else. When the switch is closed, so when the switch is closed, indicate and label the direction of the flow through wire as. So that current is to be from here, 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 and back to the battery. What happened to the motion wire X, and give the reason for your answer. So what will happen? So this is the magnetic field. Use the left hand rule for motor effect, KaDi KiMo. So align your magnetic field first, downwards, south is pointing downwards. Your current currently into my eyes, but we draw it out of my eyes into the page actually. So we just rotate it like this, and the force is to the left. So the force is to the left. So we can say the y will swing to the. So why it swing? Because we have ground. So you can to the left as the force to the left. Reason due to the field. Or you can explain further due to the catapult field by the interaction of the electromagnet and the permanent and the external magnetic field. So just two ways to change the direction of the motion. The direction of the motion. So there is two ways you can do that. First, the direction by reversing the turn of the battery. Next, change the poles. Change the or reverse this one. The external magnet poles. Reverse it. So change the direction of the current and direction of the motion. Okay. Diagram 5 demonstrates the force acting on a current carrying conductor in a magnetic field. Again, this is motor effect due to all also we can see that we have a battery. So this is motor effect. When the switch is closed, the current, but we need to draw current. So positive over here, let's say that this is connected. So this is the positive, this is the negative. So the current will flow like this into the page. This is north to south. The left hand rule. Make sure that you align the magnetic field first. So it looks like this because the south is on the left and the current is currently out of my eye. So that's moving into the page and the current we draw on the into the page. So the force is upwards. What you call this? A copper wire. Copper wire will swing upward. The rule which can be used to determine the direction of motion of the copper wire. And if the direction of current is reversed, but different observation can be made, copper wire will swing downwards or opposite direction. Draw the pattern of electromagnetic field that produces the motion of the copper wire as in A. Okay, we have wire is into the page, right? North to south, and then this one we draw. So use right hand grip rule into the page. So that means the thumb is in out of my eye. The rest of the finger is rotating clockwise. Follow the magnetic field here. Make sure they touch with each other. So we see that this region has a lot of magnetic field concentrated there. That means this is the strong region. This is the weak region. The catapult field here will push the copper rod upwards from region. So make sure that you draw is big and as much lines as possible, but make sure that it doesn't touch with each other and neatly drawn neatly. Number 3, how can the magnetic of the force can be increased? So again, based on the Fleming left-hand rule, we have two things that the strength of the magnet or strength of the current. Increase magnetic of current. Use stronger magnet. Okay. Number 5, diagram 7.1 shows electric motor. So again, KaDi KiMo, this is KiMo, left hand rule, name the type of motor shown in the diagram above. Ring this motor. What is the function of the part labeled X commutator to change direction current every half rotation, so that the direction of the rotation gonna be the same, not changed. By referring to diagram 7.1, draw the related catapult field in the diagram below. So you have to draw a straight line. So this one is counterclockwise by using hand rule. This one is clockwise by using right hand rule as well. Okay. Add more. Probably we can put one more. Make sure it doesn't touch with each other. This is already enough. This will push upwards. This one will push downwards. Okay, due to one factor that affects the speed of rotation. So we can say magnitude of current. Others, strength, magnet. Other thing is diameter of wire coil. Of resistance. Diagram 7.2 shows the type of electric motor used in a blender to grind food where a blade is attached to the electric motor. Suggest and explain the modifications which need to be done for each of the following to enable the motor to be used. For the motor to be used of the current, the magnet of iron ore needed with conductor. Or we can say it needs to be replaced with electromagnet. Explain so that the magnet to be changed, the current changes. Right here, so the field, the direction of magnet will change the same time as the direction of current. Because AC is the current is keep changing, and if we use commutator over here, split ring commutator gonna change it every half rotation. So we have a double changing here, right? So in order to make it only one type of change, so we need to change the permanent magnet. So the permanent magnet will change its direction, thus it reverses back the effect of the commutator. Why the magnet gonna be changed? Because we supply it with alternating current as well. So the poles, the direction field of the magnet itself, the soft iron core winded by the coil will change as the current will change. So we have a double changes here. First for the coil due to the alternating current. Second is due to soft iron core winded by the conductor due to also from alternating current. So these two changes are complementary from each other. Thus, it will cancel out the effect of the commutator. Thus, it will rotate it only in one direction. To increase the strength of magnetic, so or use stronger magnet, or use stronger magnet. This is previous of magnetic field. That means we cannot use stronger magnet because we use electromagnet, so just magnetic of current. Magnetic. Increase the magnetic of current. This cannot be the question. Produce concentrated magnetic something like that, magnetic field. Produce concentrated magnetic field lines. Okay, as long as we don't say a strength of magnetic field, increase magnetic of current, produce concentrated magnetic field lines. Yeah. Or we can say that the magnetic field lines closer each other. Acceptable. So let's move on to the next question. Electromagnetic induction. So a straight thick copper wire that is connected to a sensitive center zero galvanometer is moved vertically downwards in a magnetic field. So when we examine the diagram, we have a galvanometer here. So this is not motor effect, this is electromagnetic induction, dynamo. So we have to use right hand, Fleming right hand rule. Mark on the so again, Fleming right hand rule. First step, the south pole. So here, towards to the right, and then the direction of the force is downwards. So we rotate it like this. So we see that my middle finger here is into my eye, so it's out of the page. This current out of the page. Name the rule that is used to work out the direction of the current. Right hand. KaDi, KiMo. So this is KaDi. Describe the effect on this current if the wire is moved vertically upwards at a low speed. So now the wire moves upwards, the direction of current is reversed. The wire is moved vertically upwards at higher speed. Is reverse and bigger magnitude. So this is Faraday's law. The wire is held stationary in between the poles of the magnet. This current produced, not in this current produced. Okay, because we don't have relative motion, thus the magnetic field flux doesn't no cutting. The south pole of the bar magnet is moved towards a solenoid that is connected to a sensitive center zero galvanometer. So we have but we have a solenoid. Right hand rule cannot be used for solenoid. We need to change to right hand grip rule. We can use solenoid, either we can have battery or gas. Always use right hand grip rule. Mark on the solenoid that will become a south pole. So this is what we need to apply Lenz's law. So when south approaching and it should be south, it should be north. So again, if we want to use Lenz's law, why this is become south? South approaching, that means the Lenz's law state that it will oppose the changes. These changes that we do, this the action that oppose the changes. So if the south is approaching, we need to make it south away. So it must be the same pose. South and south pose will tell each other. So just remember, same pose approaching, the pose approaching. So it will be the same pose as well. So the pose will be on the side of the magnet of the solenoid. Okay, direction of induced current, right hand people. So north is on the right, so my fingers nail is pointing downwards. So let's trace this way, so the direction of reflection meter should be that. Straight three ways to increase the induced current in the solenoid. Number of turns of solenoid, increase speed of action of bar, reduce coil wire. Okay, or this one is a weaker reason, weaker answer. Probably use stronger magnet. This is more stronger magnet, bar magnet. So always put your resistor factor to the last answer as the final answer if you cannot think anymore. So you just put the diameter, the factors of resistance at the end answer as your push. So diagram 2.1 shows a bar magnet before and when it's into a solenoid. So this is before, this is when it pushed into the solenoid. Name the science phenomenon. Phenomenon or physics concept. This is electromagnetic induction. Magnetic induction. Okay. State the polarity of the solenoid at mark X. Tick right the correct answer in the box below. So mark X is here. So north approaching, so we already it must be north as well because due to the Lenz's law. Approaching, that is the change that we do. The solenoid gonna act oppose it. Push it gonna want the north pole to away, repel. So it must be north here. It must be the pole in order to make the north away from the solenoid. So north. Diagram 2.2, a bar magnet is pulling away from inside a solenoid. Mark the direction of the current flow in the circuit. So we must know the first. So south away, that means it must be opposite pole. Why? Because Lenz's law says that the change that we do, which is the south away, causing the solenoid to act against pole. So the south is away, the solenoid to be closer to it, so it must be composed because it composed attract each other. So we already do the first step here, north and south. Then we can use our right hand grip rule. Always, if you see solenoid, use right hand grip rule. So north towards the right, so the nails gonna show downwards. So we draw the current on the surface downwards. Back. So the action of galvanometer is that. By using an arrow mark the compass direction on the compass above. Okay. So magnetic field from north to south, north to south, north, south, south. This is this way towards the south. Okay, diagram 4 shows a bar magnet is hung on a spring that attached to a retort stand. The bar magnet is displaced downward and released so it can oscillate through a solenoid which is connected to a center zero galvanometer. So this is KaDi as well because we have galvanometer. What is meant by electromagnetic induction? Changes field by relative motion of conductor at no magnetic field. Okay, so that's what is meant by electromagnetic induction. You can also replace current with induced current. The bar magnet towards the solenoid galvanometer pointer for a while. Explain why the galvanometer pointer deflects induced current into induced current. Okay. State the polarity of NA and NB of the solenoid. Okay, so this is probably when the so A and B change as well. So we just pick one when now the bar magnet is approaching, which is the north pole here. So this must be north, this must be south because approaching same due to Lenz's law. A is north pole, B is south pole. If the spring is replaced by a stiffer spring, state the change to the angle of deflection of the galvanometer pointer. Stiffer become hard, so the relative motion is reduced. The velocity of oscillation is harder to achieve. In higher velocity is harder to achieve. Motion, the rate of relative motion is decreasing, and the rate of change of magnetic also decreases. So that's this current decrease. So the overall deflection decrease. If the reason induced current decreases, as the relative motion, the rate change of magnetic flux decreases. Okay. Diagram 6.1 and 6.2 show a bar magnet is pushed into a solenoid at a speed of 2 meters per second. Okay, state the physical quantity that is represented by the galvanometer induced current. It measures induced current. Based on diagram 6.1 and 6.2, state two differences that can be observed from diagram 6.1 and 6.2. So the angle of deflection, of galvanometer, and another thing is the number of solenoid. Based on the answer in B, explain why these differences occur. Okay. So both 2 meters per second, right? Okay. So the higher number of turns, the higher the magnitude of induced current. Induced current. So that is the first point. The second point, the higher magnitude of induced current, the larger the angle of deflection of galvanometer. So, name the physics law involved in 6b2. So Faraday's law involves the magnetic of induced current. Lenz's law is the direction of induced current. Explain why the direction of the current into the solenoid is upward, as shown in diagram 6.1 and 6.2. So why upwards? Due to Lenz's law. Lenz's law. The north pole is on the solenoid, left of solenoid. Because north is must be the same pole. Using right hand grid rule, the direction of the current in this current is upwards. Okay, you don't need to explain in detail. It's only 2 marks. For structure question, we need to put it in simple terms. Diagram 6.1 and 6 show that a current is induced in a solenoid when there is relative motion between the solenoid and the bar magnet. What is meant by induced current? Induced current when there is relative motion between conductor and external magnetic field. Change in magnetic field flux. Okay. Based on the direction of the current in diagram 1 and 6.2, label the polarity at the end of each solenoid in box X and box Y. This is the direction of the current from left to right, this is downwards, this is upwards. So whenever you see solenoid, make sure that you use right hand grid rule. So align your nails downwards. So your thumb shows towards the right. So that means that is the north pole on the road. Okay. Label the direction of the bar magnet in diagram 6.1 and 6.2. So if this one is north and this is also north, that means it's a. If this is south, this is north, so it's away. Okay. Based on the answers in 6b1 and 6b2, state the effect of the polarity at the end of the solenoid on the motion of the bar magnet. So, state if the bar magnet polarity at the end of the solenoid is the same as bar magnet. There is only one mark. The other one is you have to do the reverse direction. And then it's only on the nut. So the end of the solenoid is gonna be opposite as the R. And the law that applies to C1 length. So direction of current law magnetic of induced current is Faraday's law. Suggest one method to increase the induced current in coils. Other than that, increase the speed of relative motion. Other than that, and always put the factors of resistance if you want to add at the final answer. At the last point, the diagram shows the structural design of a generator and the principle used in the generator, electromagnetic. Because KaDi, KiMo, we use the KaDi here. Mark the direction of the current flow in Ws and Yz when the side Ws of the coil is displaced in downwards direction. So that Ws B. So use right hand rule, Fleming right hand rule, KaDi. Align your support and then your first downwards. So the current, the middle finger is into the eye, so that means out of the page. So in this direction. Yeah. Okay. Draw a graph to show the variation with time of the current in conductor. Okay. So this is current, time, alternate current. Just make sure that you draw it with the same amplitude and the same frequency as well. What happens to the current flows in conductor YZ when the speed of the coil rotation is increased? Faraday's law. Okay, so we have split ring here. Okay, so this is AC generator. So that's all for today. Hopefully that you understand the concept that we discussed today. So basically we touched upon the motor effect, which is the effect of force on a current carrying conductor external magnetic field, and also electromagnetic induction. We touched upon the Fleming left-hand rule, Fleming right-hand rule, right-hand grip rule for solenoid. Either it has battery or has galvanometer, it doesn't matter. As long as you see solenoid, you must use right-hand rule. We also discussed DC motor, the function of commutators, split ring commutators. This is not commutator as well. So we already discussed Faraday's law, Lenz's law, how to use that in the today. Hopefully that you understand all the concept here and strengthen your understanding. Okay, thank you.